Okay, this is the mark scheme for further mechanics checkpoint 3 about circular motion. First question, we've got a ball on a string and it's going to swing down and go through the bottom here. Okay, so it's swinging down, as you can see, this way. It's 150 gram mass. It's at one end of a light inextensible string. That just means we can figure out about the mass of the string or whether it'll stretch as it swings down. Fixed at P, held at A, and this is a 250mm radius, so they've really given us all the information we need in the diagram. The string moves down through vertical position, the mass at point B, neglecting the effective areas, and calculate the kinetic energy of the mass. Now, the temptation here is to look at kinetic energy and think, oh yeah, half mv squared, but you'll notice there's no sort of half mv squared possibility in here. So we need to start off with the conservation of energy. So we know that the energy that's at the top, the potential energy, is mgh, and that's going to turn into the kinetic energy at the bottom. So we need to do 150 grams, so that's 150 times 10 to the minus 3, times gravity is 9.8, times a height of 250 millimeters, so 250 times 10 to the minus 3. Stick all that in your calculator, and you get an answer of 0.37 joules. Calculate the velocity of the mass. Okay, so this is where you're going to need a half mv squared. So half mv squared is 0.37. So v squared is 0.37 times 2 divided by the mass, which was 150 times 10 to the minus 3. Cancel out the squared, take the square root. That gives you an answer of 2.22 meters per second. Okay, what's the centripetal force acting on the mass? Well, we've got a velocity, so we know that the centripetal force with the velocity equation is F equals mv squared over r. Remember, v squared over r here, this is the acceleration. Okay, we had a mass of 150 grams, so that's 150 times 10 to the minus 3 times 2.22 squared over the radius, which was 250 times 10 to the minus 3, which gives us an answer of 2.9 newtons. Okay, the tension in the string, okay, this is probably the trickiest bit. So there's a force upwards, which is the tension. There's a force downwards, which is the weight. So this is mg, this is T. But the crucial thing to understand here is that these are not forces in equilibrium. Okay, if it was just hanging there, they'd be forces in equilibrium, but this is swinging round. So we need an extra upwards force to provide this centripetal force. So if we write this out properly, what we've got is T minus mg equals mv squared over r. Well, we've just worked out the mv squared over r. So T is the 150 times 10 to the minus 3 times 9.8. That's the mg part of it. Plus the mv squared over r part, which we just worked out was 2.9. If you add all that together, you get 4.4 newtons. So there's 4.4 newtons up. There's only there's only 1.5 newtons approximately down. Okay, the resultant force must be upwards to provide this 2.9 newtons of centripetal force. Okay, here's a centrifuge spinning round, so we're looking at it horizontally. It does 3,000 revolutions per minute. We need the angular speed, so the angular speed is the angle it goes through in a second. So that's 3,000 times a second. Each one of those is 2 pi radians, divided by the fact that it does 60 seconds in a minute. So that's 100 pi, but don't leave your answer like that, please. 314 radians per second. Calculate the magnitude of the acceleration at a point 95 millimeters from the axis of rotation. So this is just a straightforward A equals omega squared r. We've just worked out omega up here. So 314 squared times 95 times 10 to the minus 3 gives us an angular acceleration. An acceleration of 9.4 times 10 to the 3 meters per second squared. Okay, so a very big angular acceleration. A very big acceleration. Okay, this is a kind of reason that things are separated out. It's almost like putting them in a very strong gravitational field. State the direction of the acceleration. Okay, this is a standard GCSE question, so hopefully you can do this one. The direction is towards the centre, or the axis of rotation, if you like. Okay, number 3. So in a football match, a player kicks a stationary football of mass 0.4 kilograms. 0.44 kilograms gives it a speed of 32 meters per second. Calculate the change in momentum of the football. Okay, well that should be fairly straightforward. Hopefully, delta mv is 0.44. It's gone from 0 to 32 meters per second, so that's a change of 32, and that gives you 14 Newton seconds, or kilogram meters per second, if you like. The contact time between the football and the footballer's boot was 9.2 milliseconds, so calculate the average force. So the average force is simply the change in momentum divided by the time. So that's 14 divided by 9.2 times 10 to the minus 3, which comes to 1.5 times 10 to the 3 newtons. Okay, a video recording showed that the toe of the boot was moving in a circular arc of radius 0.62 meters, centered on the knee joint, so the top of the leg's not moving. This is a pretty funny way to kick a football, I think, but the top of the leg's not moving, but there's an arc centered around the knee here. The force of impact slowed the boot down from a speed of 24 meters per second to a speed of 15 meters per second. Calculate the deceleration of the boot. So we've got the change in velocity divided by the time, and the change in velocity, it's gone from 24 to 15. This is in the same direction, so that's a change of 9 in a time of 9.2 milliseconds. So that's 9.2 times 10 to the minus 3. So 9 divided by 9.2 times 10 to the minus 3 gives us a deceleration of 9.8 times 10 to the 2, or 980 meters per second squared. Calculate the centripetal acceleration of the boot just before the impact. Well, we've got this is just before the impact, so that's we've got a velocity, so our best equation to use here is A equals V squared over R. So just before the impact it was travelling at 24 meters per second, so that's 24 squared divided by 0.62 gives us an acceleration of 9.3 times 10 to the 2 meters per second squared. Okay. For the next bit, what you need to understand is that this acceleration as the boot swings round must be coming from the knee, and you've got to be pulling upwards on that leg. So when the leg's down here somewhere, there's a force upwards pulling on the bottom of the knee upwards, which obviously means pulling on the top of your leg downwards. So discuss briefly the radial force. So we're not worried about the force backwards on the boot when you kick the ball. This is just the force along this line. Just before the impact and during the impact. So all you need to say for this is before the impact, force towards the knee, and then during the impact the force reduces because the speed's reducing, so the V squared over R is reducing. Okay, obviously you might be thinking, well, surely there's a force on the foot when you kick the ball. Yes, there is, but that's a force tangentially, okay, in this direction, not a force radially in this direction. Okay, so this is the washing machine question. So we've got a pulley on the motor A shaft that has a diameter of 24 millimeters. Be careful here, this is a diameter of 24 millimeters. And the motor is running at 50 revolutions per second. Calculate the speed of the belt. Various ways you can do this, but maybe V equals R omega. So the radius is 12 times 10 to the minus 3. And our omega, 50 revolutions per second. So that's 50 lots of 2 pi radians per second, and that will give us an answer of 3.8 meters per second. The centripetal acceleration of the belt as it passes around the motor pulley. Sorry, I've put the diameter in the wrong place over here, by the way. This is the motor pulley, so this is the diameter here that we're talking about. So the centripetal acceleration, well, again, this is just an A equals V squared over R. So 3.8 squared divided by the radius. Here's the radius, 12 times 10 to the minus 3 meters. And that gives us an answer of 1.2 times 10 to the 3 meters per second squared. Okay, here's our multiple choice questions. If we understood the one earlier, this one should be fairly straightforward. So the pendulum comes down here, it swings through the middle. Which of these is the correct equation for the force at the bottom? So we've got a tension T upwards, we've got a weight mg downwards, but that needs to provide a centripetal force to keep the thing going round a circle, otherwise it's just going to carry on like in this direction. So the resultant force towards the centre of the circle is T minus mg, and that's got to be equal to mv squared over r, or in this case r is L. So that gives us this answer here. So the first one is D. Okay, we've got a girl of mass 40 kilograms on a roundabout. She's 2 meters from the vertical axis of the roundabout, which rotates uniformly with a period of 3 seconds. So here she is. She's 40 kilograms. She's got a distance of 2 meters from the center. The roundabout's going round in 3 seconds. We're looking for a force. It's horizontal, so there's no trap here. It's not the zero because there is a force horizontally to hold her into the circle. We've got a period, so probably an omega is our best approach to this. So we've got F equals m omega squared r. So the mass is 40. The omega, it takes 3 seconds, so that's 2 pi in 3 seconds. That's squared times the radius of 2 meters. If you put that into your calculator, you will get about 350 newtons, which gives you the answer B. Number 7, for a particle moving in a circle with uniform speed, which of the following statements is incorrect? Okay, the velocity of the particle is constant. Well, that's clearly not true. The velocity is not constant, the speed's constant, but the direction is changing, so the answer's A, but we probably should just check the other ones just in case. We've had a little bit of a brain fade. So the force of the particle is always perpendicular to the velocity. That's true, isn't it? If it's going around in a circle, if it's in this direction, the velocity is going that way, the force is going that way. There is no displacement of the particle in the direction of the force, no, because it's going perpendicular to the force. The kinetic energy of the particle is constant, that's a half mv squared, although that looks like it might be a vector quantity. Of course, it's an energy, so it's not. So the half mv squared is a constant all the way around. Number 8, a fairground roundabout makes 9 revolutions in 1 minute. The angular speed, well, that's 9 lots of 2 pi in 60 seconds. So you've got to do 18 pi divided by 60. Which is near enough 1, so the answer is C. Number 9, the angular speed of a point on the Earth's equator. The first reaction usually to this question is to think, I haven't got enough information there. You haven't told me how big the Earth is. You haven't told me how long it takes to go round. Okay, well, hopefully what you realise is that one of those things is irrelevant because it doesn't matter how big the Earth is because we're talking about the angular speed. And the second one, how long it takes to go round, hopefully you might know how long it takes the Earth to go round. So we've got 2 pi radians in a time of 24 hours times 60 minutes in an hour times 60 seconds in a minute. And that gives you an answer of 7.3 times 10 to the minus 5 radians per second. Doesn't matter if you're on the equator actually, or if you're in Birmingham or anywhere else. Okay, that's going to be your angular velocity. Okay, and our last one. So the model car moves in a circular path of radius 0.8 meters at pi by 2 radians per second. So that's pi by 2, remember, is 90 degrees. What is displacement? 6 seconds after passing point P. So it's here. In 6 seconds, it's going to do 6 lots of pi by 2 radians. That's 3 pi radians. So 3 pi radians is the whole circle is 2, plus another semicircle is 1. So it's going to get to there. So fortunately, you haven't got some sort of complication of a calculation. If it was up there or somewhere, it'd be a bit of a tricky question. Okay, you'd have to work out this distance here, but fortunately it's just straight across the circle. So it's 1.6 meters away from where it started.